So we want to find the Laplace inverse of f of s. And when you're given this, it's really just a couple of algebraic tricks in order to get into the position where simple Laplace inverse cases can be applied. And so the first thing we need to do is simply factor out. So the key is really simply to apply partial fraction decomposition at this point, because after that, once we get it into a simple expression, or simple enough to apply the rules we're given in the conversion tables, then we simply directly apply them. And so multiplying on both sides, we have 5 is equal to as squared minus 4a. And remember, so we're multiplying by the denominator on the right hand side. So s plus 1 times s minus 2 is s squared minus s minus 2. Okay. In fact, I'll make it simple. I'll write it right here. We have no s squared on the left side, so we look at all the terms of degree 2. There's no left-hand side, non-zero left-hand side that's of degree 2, so we can conclude that a plus b plus c is equal to 0. We can also conclude that negative bs plus 3cs is 0 because there's no s. And finally, negative 4a minus 2b plus 2c is equal to something. It's 5. So because there's a term of degree 0, it's 5. I'm going to convert this into matrix all the way over here, okay? Row equivalent to what? Let's multiply the top row by 4 and add it to the bottom row. So that's 0, that's 2, that's 6, and 5. And so let's multiply the middle row by 2 and add it to the bottom row. So we have 12 over 5 here. Now I'm just going to go ahead, because this row is in the proper form, go ahead and divide everything by 12. So we have 1 and 5 over 12. And I'm going to, let's change this to a positive. That means this will be a negative. Okay. I suppose there's a lot of, I want to really take shortcuts, but I don't want to be confusing. So negative this row added to this is what? It's 1, 0, 1, negative 15 over 12. And negative this row added to the top row. Okay, so then we just apply the Laplace inverse. So let me just make some new space here. Okay, we got some space. So let's copy this down. So we have what? We have that f of s is equal to, so the Laplace inverse of this whole expression is the Laplace inverse of those individual expressions because of the linearity of Laplace transform. And I think even it can be considered a homomorphism, and this is our answer. So it's simply a matter of getting it to a simple enough expression to where you can directly apply the Laplace transform rules. And curiously, this same thing, s squared f of s, out of curiosity, minus, I believe that's right. So we can recall that the Laplace transform of some, well, I mean, because it's a linear transformation, so if we apply on both sides the inverse of this, then it's, well, these, because it is a linear transformation, we have what d square f, oh, I should make this into an s, I meant s, sorry. D, and, you know, let's assume that f of 0 is 0 and f prime of 0 is 0. So then these are just 0. And so we have this expression here equal to that. Well, let's apply the Laplace inverse to both sides just directly to that, okay? That's what we're doing. Well, then what does this expression, what is it equal to? Well, if we assume that these are 0, then it's equal to that. So we have d squared f ds squared minus 4 some function f, right? Because we're just doing this, and assuming it's a continuous function. Oops, sorry. Well, it's still, it yields a function. I mean, the Laplace transform is a integral operator, right? So the inverse yields some function. So we just call f. And what does the right-hand side yield? Well, that's just 5, Laplace inverse of that, 5e to the negative t. Interesting, because this looks like something that you can use the method of undetermined coefficients to solve. Clearly r, right, r is plus and minus 2. And so our conclusion is what? That homogeneous equation is. Does that look familiar? Now, in the for the particular function, I mean, clearly we have, let's say that f is equal to a e of negative t. Well then, and the left-hand expression is dt squared minus just f, so we have e to the negative t minus 4a e to the negative t, which is equal to negative 3 a e to the negative t, right? And that's equivalent to this. So if we divide both sides by e to the negative t equal to negative 5 over 3. So we can conclude that our particular function, which is exactly the solution to the previous one, except that we have these constants here. So that's interesting that once we make that assumption, that we get essentially a class of functions, right? Because